Hello, my name is Renato Montrose, and today I'm going to talk about uh, Fourier transform, the application basically of Fourier transform. So there are many scenarios where we apply Fourier transform today in current technology, but today we basically going to um, show how this is being used to do image compression. Before we get started, let's see why image compression is important. It's not a topic about image compression, but we just want to see why is it important. So one of the reasons why we do image compression today is because we might want to um, store space, right? Because we have so many data today, and we want to have enough space to store our data. So we do image compression to have more space to save our data. And we also do image compression to to for live data, right? So let's take for example that uh, let's say for example we're shooting a video, right? And this video that we're shooting, we want this video to be available for end user while we're shooting it. This is not data that we're going to store and then manipulate it later. This is the data that we have to manipulate um, live. It is live data, right? This is an important case that uh, we want to use image compression. Okay, and a lot of applications do this today, and we just don't want to list them, right? But there are many applications today that did image compression. So what we are going to do here. So we're going to take a signal, right? And we're going to apply the transformation to the signal, basically a Fourier transform. And then we are going to filter it, right? Because once you apply the Fourier transform to it, what it's going to do, it's going to uh, convert your signal into a frequency domain, right? And that frequency domain, you're going to have uh, a series of frequency where we can have the low frequency and the high frequency, right? So we're going to filter this image, take only the high frequency, and then we're going to reconstruct the image via inverse discrete Fourier transform. So let's go ahead and see what these are. Okay. First, let's talk about the Fourier transform. Fourier transform, given the function f, right? So the Fourier function transform of that uh, function is given by f of x, the integral of f of x e minus I x c dx, right? And what we want here, we want f of x to belong to L1. Belong to L1 means that it needs to be absolute value integrable. And we want it to be we want that integration to be less than infinity. So this is a basically the Fourier transform of a function. And this fit our scenario because uh, we have discrete amount of data, right? So basically, the integration of those data is going to be less than infinity, right? It's not an infinite amount of data. So this is one scenario that we can apply Fourier transform for our case of image compression. Now, since we have a discrete amount of data, we're going to apply discrete Fourier transform. And what is that exactly? So it's a map that take uh, a set of frame that take x and map it to x hat, right? So x is the signal that we receive. Any type of system that is going to do this manipulation, this transformation. So it receives that signal x, and it's going to transform it to x hat. X hat is a frequency domain object, right? So that's what the discrete Fourier transform is. So where uh, we have xc equals e to the 2 pi over n, and by the Fourier, by the order equation, right? So we know this is exactly cos 2 pi over n plus I sine 2 pi over n. Whenever we refer to this, that's what we mean by this, by xc. This is its value, right? So from there, this is what we do for the discrete Fourier transform. We iterate over every um, element of the signal, right? And that's exactly the operation we do with it here. This is an example of this transformation we have here, right? These are the input, right? It takes x, and the transformation map it to x hat. Now we are going to talk about the inverse of the discrete Fourier transform. Basically, what we see, this is one of the steps that will be performed in our conversion program, right? Since we're going to apply the inverse discrete Fourier transform, we need to go over it and see what is it exactly, right? So if we think of the incoming frame, the signal that we receive as column vectors, right? In the output, right? X and x hat, we consider them as column vectors. So what happened here? So we have a function that the x and return x hat from this. This function here is our discrete Fourier transform. That's what it do. And we said that for any integer a, uh, we have the summation here equals n if x to the power of a equals 1, and otherwise it will equals to 0. So from there, we have f hat equals n I is the identity. We are not going to prove this because it's out of scope, right? But we use this fact here to compute the inverse discrete Fourier transform. Remember that we said that we're going to use the discrete Fourier transform to reconstruct the image, right? So now we're going to have our x equals 1 over n f hat x hat, which is this, kind of similar to the discrete Fourier transform, but this is the inverse because you see this has the 1 over n and it doesn't have the minus j here. Okay, so this is x hat j, not x hat like the discrete Fourier transform, because um, uh, x hat is basically the output of the discrete Fourier transform, and we're going to use it as the input for this and output x. So that is our inverse discrete Fourier transform here. All right, and I need to note that f hat is basically the complex conjugate of f. Okay. Now, the Fourier transform itself is a very expensive operation, right? So because it will really call the transcendental central processing unit support for c to the minus jk, right? That we have from our discrete Fourier transform, right? So what I mean by that, if we go to here, if we go here, we see here. So it's going to call that, and this is very expensive operation because it is cos 2 pi jk over n plus I sine 2 pi jk over n. So and it is going to do this for every single element in the signal. Suppose that you have let's say we have a 10 by 10 signal. This is a very small signal, but applying discrete Fourier transform to that signal is going to be very expensive, right? So it's going to do basically n squared multiplication on each element, right? So 10 by 10 would be 100, and we're going to do n squared operation on each of element, right? Element index 0, index 1, index all to index 99, right? So this is not cheap. So we need a way out. So the way out is apply the fast Fourier transform, right? So the fast Fourier transform basically is this algorithm, right? We basically going to split our signal, right? That's what we call divide to conquer. We're going to split the signal into even and odd indices. Okay, so we make n equals to m, and we split the signal. And on each of this signal, like if suppose that we get a signal of length 4, right, of 4 frames, right? So that's going to be 0 to 3. That's going to be our indices. That's total 4 frames, right? So we're going to consider this is divided into two sets, two signals, right? One signal is going to contain 0 and 2, and the other signal is going to contain 1 and 3, the odd indices, right? And on each of these, we're going to split this again into uh, uh, add and even indices to apply the discrete Fourier transform, right? So that's what we call the divide and conquer, and that's what we will be doing in the next few slides and in our demo. All right, now let's dive into the demo. So what we're going to do here in our demo, we're going to take an image, basically, right? Let's say we're going to take an image from the input folder, right? This is the Afghan girl that we pick up on the internet, so I don't own the right to this image. So and we're going to take this image and apply our algorithm to this image to compress it. As you can see, this image is of size. Let me actually open it. This image is of size 62.3 kilobyte. Okay, and we're going to transform this image. Let's clear it out and store the result in the output folder. Let me clear this out, and so that we can let me see. Um, yeah, so we're going to apply our transformation and store the compressed image into this. But note that this image is a low frequency image. So there is not much to compress, but we're still going to apply our transformation to it to see what happened, right? So let's go ahead and open our program here. Our program is written in Python, and the IDE integrated development environment that we use is Visual Studio Code. So if you want to run this, because I will make the program available online. So if you want to run this, you can use any IDE of your choice, PyCharm or any other IDE. So what this does is it's going to take the image from the input folder, right? We're going to take the image, right, from the input folder and then apply the fast Fourier transform to it. This is exactly what we did. That's what I was showing you, the divide and conquer method. So divide into even and add indices, and we loop through them and then return it. Uh, so once we get that, then we're going to take this output from the fast Fourier transform. We're going to sort it, right? Because it's going to be um, in frequency domain, right? So since we're going to take the best, the highest frequency, so to make our program less expensive, and we sort it first, and then from there we can take the best one and throw away what we don't want, right? So that's what we do here. We sort it, and we find all the small indices, we threshold it, and then we'll apply the inverse Fourier transform to it to reconstruct the image. And once we reconstructed the image, we just display it and store it. All right, let's go ahead and see what's going on here. So our output folder is cleared, is empty, right? And let's run the image, see what we get. Let's run the program, right? Program is running. All right, here we go. So this is the first image we have. In this image, we keep 10% of the best Fourier coefficient. We throw away 90% of them. And you see this image is still a good quality image, right? Almost similar to the original version. This is the original version, and this is 10% of the original version, right? Right, let's keep on processing. Let's see what we get for 5% of the original version. Let's process more here. That's the image quality that we have with the compression um, to keep only 5% of the highest frequency of the original image. Now we're going to keep here only 2%. So things start getting bad here, right? But you can still see what's going on. You can still see the picture, right? And if we keep only 1% of the original image, that's what we get. So, which is not good at all, right? But still, uh, if you see the previous image, you can identify it, right? So that ends our program. Now let's take a look at the output folder and see what we have. All right, we have our data here. So look here, right? So this is the one that we can take, we keep 10%, right? So remember the size of the image was 62.3. Now we were able to convert it to 53.7. This is an image with low frequency spectrum, and we were able to basically still compress it and remove about 10 pixels, 10 kilobyte. 10 kilobyte is enough data. You still keep the dimension. Right here, we are able to compress this image and we reduce it to 47.7 kilobyte from a 62.3 kilobyte, right? And this image quality is not too bad, right? It's not too bad for such a compression rate. So same here, this is the other image. This is the 2, right? This is the image that we get with only 2%, right? And if you see here, this only 2% here is 44.4 kilobyte of data from 62.3. All right. So that ends our application of a Fourier transform on for image compression. Thank you.